please don't write, just watch and listen. If this is your second or later time watching it, please have your note sheet ready so that you can take notes as we go. And please watch and listen to the lesson and don't just wait for me to write things down. Appreciate it. Now, I know you can read, so I won't take the time to read all of this through for you, but I do want to point out a couple of things. This does talk about the idea of an inverse function being an undoer. This is similar to what we've already done in class, and I'll show you some examples of that in a moment. And there's also a switch and solve method, which we'll talk about as well. This introduces a couple of terms that you should already be familiar with, but just to review, a relation is simply a set of points. Any set of points is a relation. Now, this relation is not a function because for the x values, there's more than one y value. For the x value 3, there shows more than one y value. A function is a special relation where for each x value, there's only one input or output, or only one y value. So the vertical line test is something else that we talked about today that you can use to identify a function. The math notes below talks about the vertical line test, which should be a review to you as well, but let's take a peek at it. The vertical line test for functions. This says if one or more vertical lines intersect the graph of an equation at more than one point, then the equation is not a function. So this is a function. Remember, you can drag your pencil across the paper and see if the pencil crosses the graph more than once. This is not a function because here the pencil crosses at 2 places, here it crosses at 3 places, and so on and so forth. So we have some problems here to help us with this concept. This says, what is the equation of the vertical line that can be used to show that this relation is not a function? So we have these 3 points here. We have a graph there. So we have these 3 points at 3, 6, and we have a point at 5, 7, and we have a point at 3, -1. If you're just talking about those 3 points, this asks what is the equation of a vertical line that can be used to show that the relation is not a function. So if you drug a giant pencil across the graph here, at what vertical line could you say that this is not a function? So this vertical line here goes through 2 of the points, showing that for this x value, which is 3, there's more than one y value. So what we're looking for here is x equals 3. That's the equation of the line that shows that this relation is not a function. Anytime during this video, if you're watching this for the second time or later, that you need to pause it or rewind it so that you can have time to get this information on your paper or look at it again and soak it in a little bit better, feel free to do that. Problem 351 talks about another relation, another set of points. It says let f be this relation, 2, 6, -5, 1, and -7, 4. Is it a function? And explain. Well, for each x value, is there only one y value? So we would say yes. It is a function because for each input or x value, there is only one output or y value. All right, now B asks you to add a 4th point so that this is not a function. So if we had another point in this set of points that had an x value that had a different y value, for instance, if we had the point 2, -1, or 2, 5, or 2, 100, or 2, anything, or if we had the point -5, 3, or -5, -2, or any y value for -5, in addition to the one that's already here, or if we had -7, 0, hopefully you get the point. Any point that has these x values, any of these x values that gives you a different y value, we'll make that no longer a function. So for 3-52, we're looking at an inverse that is not a function. So now we're going to talk about Danny and Regis. This is that Danny was having trouble finding the undo function, or the inverse, for g of x equals x squared. So he graphed y equals x squared and used a carbon copy method to get the interchanged graph to the right over here. So this talks about the carbon copy method. I'm going to demonstrate this for you. It says to go over the graph heavily several times with your pencil, then fold along the line y equals x and press to transfer the graphite. You'll get a pale inverse that you can see and preferably color over with a colored pencil. So here's the graph. Oops. There's the graph. There's the line y equals x. And I have colored over the graph y equals x squared heavily with a pencil. So if I fold this along that line y equals x, very precisely, because precision is everything, and I press down really hard, hopefully we'll get a carbon copy here. I'm going to kind of press down and hope that the graphite will transfer to give me a pale image. A darned pale image, but we've got something here. I don't know if y'all can see that. Can you see the pale image here? The graphite is showing us the inverse. So I'll trace over that. The graphite image as it shows on the graph that I just used the carbon copy method. You can see that it is very similar to the one up on the lesson sheet. So you can try that with any example or any problem that you want to try the carbon copy method. It does work. All right, so he says, aha, now I know the inverse function. What equation do you think that he was thinking of? Well, let's think about this. This is the equation, y equals x squared, where if x is 1, x squared is 1. If x is 2, x squared is 4. So y would be up there. So over here, if you're turning this around, then let's think about our ordered pairs here. This would be 1 and -1. This would be 4 and -2. Or if you look at the positive version, you have 1 and 1, or you have 4 and 2 up here. So if you flip those values around, what are you flipping? Well, you're flipping your x and y, so he's probably thinking of the function x equals y squared. Okay? X equals y squared would be this graph right here. So Regis says, but wait, x equals y squared is not a function. Why do you think he's saying that it's not a function? Why is this not a function? Is anybody thinking about the vertical line test that shows that this is not a function? Can it still be the inverse without it being a function? Well, sure, we know that's the inverse, but it's not a function. So Danny says you're being picky. It works, doesn't it? But Danny was wrong. Why is the inverse not a function? And here we can talk about the fact that it doesn't pass the vertical line test. It doesn't pass the vertical line test. Are we okay so far? Pause if you need to. I'm erasing. Okay, so how can we make it a function? Because if it's the inverse, we want it to be a function. So let's look at what our options are here. This says when the inverse equation obtained by switching the x and the y is not a function, we can make it a function by restricting its range. So if f of x equals x squared, then find the inverse and restrict its range so the inverse is a function. So we're looking at this graph again. And we're looking at the inverse of this. So we're looking at x equals y squared, which is this graph right here. This is if we solve this for y, which means we would take the square root of this. If x equals y squared, and we solved it for y, we would take the square root of both sides, which would give us y equals positive or negative root x, which is not a function. We can see that. But if we choose only the positive branch for the inverse function, then we've restricted the range, which means if we only choose this branch, or we can only choose the negative branch, but if we only choose either the positive or the negative branch, then it is a function. So if this negative branch wasn't even there, then now you have a function. It would pass the vertical line test. So you can restrict the range, or the y values, of the inverse to make it a function. Here is the restricted range on this one. Y is greater than or equal to 0. So this only exists where y is greater than or equal to 0. Okay? So for each of the following, graph the original function and then find the equation of the inverse and draw the graph of the resulting inverse function. Then state a range that will make the inverse a function. So let's look at that on the graph paper. Notice, first of all, that these two equations, and I know that you can probably see these better on your own paper than you can on the board on this video, but these two equations are simply the parent graph of x squared transformed. Hopefully you remember that if you're subtracting 2 inside the parentheses with the x, this is a horizontal translation 2 units to the right. So this is x squared translated 2 units to the right. So what is this transformation? This is also the basic x squared parent graph, but this one's translated which way? X squared minus 4, if you're subtracting 4 from the whole thing, you're translating down. So we're translating 4 units down. Okay? So this is g of x equals x minus 2 squared. And this is h of x equals x squared minus 4. Hope I'm going to take that away. Oh, good. So that does show up with the graph paper there. So we want to graph these. We want to graph our g of x and our h of x. So our g of x is our basic x squared translated 2 units to the right. So our basic x squared curve would be, and I'm plotting the points 1, 1, and 2, 4, and negative 1, 1, and negative 2, 4, because I know that those are points on my basic x squared curve. So if I'm translating that 2 units to the right, then I have this graph. So this is the graph of g of x. This is the graph of the basic y equals x squared parent graph. Okay? So if we then want to graph h of x, which is the basic y equals x squared graph translated 4 units down, then I'm just dropping this graph down 4 units. Hopefully I'll have some graph paper to do this on. All right. So they ask you in the problem to find the equation of the inverse and then draw the graph of the resulting inverse function. So we talked in class about undoing these functions to find the inverse. So if we're looking for the inverse of g of x, if we're undoing g of x, then we need to think about what was originally done to g of x, and then we need to reverse that. The last thing that was done to g of x is the square. So we want to start our undo process by taking the square root of x. And remember, anytime you take the square root, you end up with a positive or negative, But we know that we're going to need to restrict the range anyway, so we'll just keep it positive. Okay? The first thing that was done to the g of x equation is minus 2. So the last thing that we're going to do to the inverse is adding 2. Okay? So the basic square root of x equation, which if you still have your parent graph sheet from the beginning of the year, looks like this. And we're moving it up 2 units by a transformation, then we are looking at this graph. The dotted red graph is the graph of the inverse of g of x, which is root x plus 2, but we want to restrict our domain, which is why it doesn't come down here also. Technically, the graph would come down here also and would be a parabola, just turn to the side and shift it up 2. But since we need to restrict our domain, or our range, so that it's going to be a function, we're going to restrict our domain to where y is greater than or equal to what? Look at the dotted red graph where you have the inverse of g of x. Y is greater than or equal to what? Hopefully you came up with 2. So let's do the same thing for the h of x. Okay? If we're going to undo what happened to the h of x equation originally, then we have h to the negative 1 of x. And we think about what originally happened to the x in h of x. Well, the last thing that happened was 4 was subtracted. So we're going to start by adding 4. And in the original equation, the first thing that happened was x was squared. So the last thing that we're going to do is take the square root of the whole thing. So this is our inverse function. And here we have the same graph, but here we're sliding this one. Remember, if you're adding to the x, basically in parentheses, then you're going to be moving 4 units to the left. So this red graph, if it started here and I moved it 4 units to the left, then it would be here. And you can punch all of this into your calculator and graph it and see the graph. And we will practice that in the classroom. But here we are looking at the graph of, this was the original graph of h of x. This is the graph of the inverse of h of x, which is root of x plus 4, all underneath the square root sign. And we have restricted our domain where y is greater than or equal to what? This graph only exists for positive values of y, so where y is greater than or equal to 0. So I know that's a lot on one graph, but this is for 3-53 parts A and B. Part A is in red, the graph's in red, and part B is in green. Feel free to pause and rewind if you need to. We have just a couple more. All right, so 3-54 talks about finding the equation of the inverse. And this says, if x appears only once in a function, you can undo it or find its inverse easily by doing the reverse operation in the reverse order, which is what we've just done to those other 2 equations. For example, if you had the original function f of x equals x plus 3 divided by 5, which first adds 3, then divides by 5, its inverse will first multiply by 5, then subtract 3. So the undoing is pretty easy if you only have one x in it. But if x appears more than once, an algebraic method called switch and solve must be used. This method is shown in the math notes box below. Let's take a look at that a little more carefully. Finding the inverse by switch and solve. This is the equation that we're looking at, f of x equals x plus 3 divided by x. So if you had that, then you can start out by simply switching places with the x and the y. So the x's become y's, and the y becomes an x. So now we're looking at x equals y plus 3 over y. So we want to try to solve this for y. So we first try to get all the y's in the numerator on one side. So we start by multiplying both sides by y, which cancels those out. And on the left, you now have xy equals y plus 3. Then, if we subtract y from both sides, then we have xy minus y on the left equals 3 on the right, which is good. Now we have all of the y's in the numerator on the same side. So we can factor out a y here, which gives us y times the quantity x minus 1 equals 3. And then to solve for y, simply divide both sides by x minus 1. So you end up with the inverse of function of f equals 3 divided by x minus 1. All right, so we're going to practice that for a couple of these, and then we'll be done. All right, this is to use the switch and solve method to find the inverse of g of x equals 2x over x plus 2. So we're going to start off by calling g of x y, and then we'll switch places with the x and the y's. So the y becomes an x, and the x's here become y. So I have 2y divided by y plus 2. Okay? So again, I want to get this y portion out of the denominator, because that's certainly not ideal. So I'm going to multiply both sides times y plus 2. This is the fraction buster method. So these will cancel out, and I have x times the quantity y plus 2 on the left, and I have 2y on the right. I want to get all my y pieces together, so I'm going to go ahead and distribute the x through the parentheses on the left. So now I have xy plus 2x equals 2y. So I want to get all my y's to one side, so I'm going to subtract xy from both sides. Okay. So those are going to cancel out. And on the left side, I now have 2x, and on the right side, I have 2y minus xy. So I'm still trying to isolate the y. So if I factor the y out of the right side, then I still have 2x on the left. On the right side, I have y times the quantity 2 minus x. I basically undistributed on the right side. So my last step in solving for y here is to divide both sides by 2 minus x. Which will cancel those out, and now I have y by itself, which is ultimately what we wanted. So we have y equals 2x divided by 2 minus x, which is the inverse. So we have the inverse g of x equals 2x divided by 2 minus x. It doesn't really look that much different from the original, but you can see that that is what it is when you use the switch and solve method. Okay? So 3-56 is a more general question, and if you need to pause this and get this down, you can. I'm going to erase it so it's not showing up on top of everything. Okay, so if f, the negative 1, is the inverse function of f, is f the inverse function of f to the negative 1? So are the inverses of each other? Do they undo each other? So think about it. If you undo something, then if you undo that, does it take you back to the original? So let's think about the example that they gave us above. The example they gave us above had f of x equals x plus 3 over 5. So when we undid that, we looked at what happened to the original equation and then did all of that backwards. The last thing that happened to this equation was dividing by 5. So we started by multiplying by 5. And the first thing that happened to this original equation was 3 was added. So we're going to finish by subtracting 3. So we had the inverse function of f is 5x minus 3. So now what if we undo this? If we undo the inverse, does it take us back to f of x? If we undo this function, the last thing that happened to this one was 3 was subtracted. So if we start by adding 3, and the first thing that happened to this equation was 5 was multiplied. So if we finish by dividing by 5, then yes, it does take us back to the original. So you can say yes. Undoing the undo does take us back to the original. And you can word this however you want. You can say that they undo each other. That probably sounds a little bit better. So we have one more example here. This says if the inverse of f of x is x cubed plus 6, then find f of x. So let's undo the inverse just like we did there. The original equation here is the inverse of f of x equals x cubed plus 6. So let's undo it. If we're going to undo this, we need to think about what happened to the original equation. Well, x was cubed, then 6 was added. So we want to work backwards. If plus 6 is the last thing that happened, then we want to start by subtracting 6. Okay? And then the first thing that happened here was x was cubed. So how do you undo a cube? Well, how do you undo a square? You undo a square by taking a square root. So you undo a cube by taking the cube root. So there's f of x.